Thank you for the introduction, and well, thanks for inviting me. Right, so I'm going to talk about kinetic field theory, which is still a fairly new approach to cosmic structure formation. And I think we've been working on it for the last 6 or maybe 7 years now. And today I will take you through the formalism, so give you a thorough introduction into the formalism. And then I'm going to share some of the most important results that we have obtained so far. And in the second part of my talk, I will then focus on the advantages that a particle-based approach offers as compared to other analytical approaches which are based on fluid dynamics, for example. Right, so trying to continue. Right, so when we're talking about structure formation or nonlinear structure formation, what we actually want to describe is the evolution of tiny density fluctuations in the early universe up to the web-like structures that we see today, like so, for example. And well, we need a fundamental understanding of nonlinear structure formation in order to answer open questions that we have in cosmology. For instance, what is the nature of dark matter and dark energy? Or, for instance, how exactly do virialized or nearly virialized structures such as dark halos form, and especially such peculiar features like the self-similarity of the density profiles of dark matter halos. And another reason is being able to interpret the wealth of high-quality data that we're going to receive from, for instance, weak lensing surveys. And for that, we will need reliable predictions for the matter power spectra, and to extract the full wealth of signals, we'll also need higher order power spectra. And in addition, we need to understand the effects of baryonic physics on structure formation and the matter power spectra. Right, so the tools that we have available to study structure formation are, for one, numerical and body simulations, which allow us to simulate structure formation really far into the nonlinear regime. They produce great results, but they are also limited by box sizes, by the resolution, and especially by computation time. So they're not really suitable to scan large parameter spaces if we want to check for modified theories of gravity, for instance. Also, if you want to compute higher order spectra, this gets increasingly hard. So we really need analytical approaches to study structure formation, and of course there are some. So one that works really well is the halo model, or the halo fit motions, to compute the matter power spectra, and we need to assume something about the halo profiles and the halo mass function. For instance, if you study modified gravity theories, you might not know these, right? And for the halo model to work really well, to produce good results for the matter power spectrum, for example, you also need to calibrate with numerical simulations again. Another analytical approach is the Eulerian standard perturbation theory, SPT. It's based on the fluid equations. And because it is based on fluid equations, it has a notorious shell crossing problem, because dark matter is described as a fluid, and it is not. And in a fluid where you would normally form shocks, dark matter streams would just cross, and you will have a problem in describing this crossing of streams. I will talk about this in more detail later on. And so, because of the shell crossing problem, SPT is largely successful in the linear or mildly nonlinear regime, but when it comes to the nonlinear regime, the perturbation theory just breaks down. So the same thing happens for Lagrangian perturbation theory. So I'm going to talk about kinetic field theory today. And kinetic field theory is based on following particle trajectories in phase space. So we start out with a phase space distribution of particles in which we discretize. So we're really following individual particle trajectories, but we treat the whole thing as a particle ensemble always. And we just follow the trajectories of these discretized particles in time. And only after this evolution would we compute macroscopic properties, like for instance, the density power spectrum. And the nice thing about working in phase space is that trajectories just cannot cross. So we will not have a problem with shell crossing. And the main object of the theory is a generating functional, which is probably familiar to you from quantum field theory. And it's just a path integral over basically a probability distribution of some field. So this is basically the general expression for a generating function. In KFT, we don't work with fields normally. We replace the fields by point particles instead. So we are talking about particle positions and particle momenta. And so for the generating functional, which for KFT looks like this, I hope you can see my cursor, right? So we introduce an additional source field J, which will allow us to take functional derivatives later on. So I will show why we want to do this. But basically, so our generating function is like this. We have a path integral over all possible particle positions and momenta. We have some probability distribution of particle positions and momenta, and we have this phase factor, which incorporates the dynamics of the system. So what we do is we then rewrite this probability distribution. We split it into an initial particle distribution of positions and momenta in phase space, and some probability, some transition probability of particles going from their initial positions to some final positions. And because we're working with a classical system, we can replace this transition probability by a Dirac delta function, which will simply single out those trajectories which obey the classical equations of motion. Okay, and so this d gamma is just a shorthand notation of the integral over the initial phase space positions and momenta. And we can then just take the integral over all possible paths, and the Dirac delta will ensure that we can only, in our dynamics, have those trajectories which correspond to classical equations of motion. And this is the expression basically that we start off in KFT. So what do we have? We have an integral over particle positions and momenta, some initial conditions, and particle dynamics. The initial conditions can be fully specified by an initial power spectrum, which we usually take from the cosmic microwave background. And it's well known to us. And the dynamics here include the solution to the equations of motion. And we usually split the solution into an inertial motion, so just freely moving particles, and then a part which includes interactions between particles. And so the dynamics of the particles will simply be described by Hamiltonian dynamics, where we have a kinetic and a potential term, and the potential is sourced by some overdensity. Okay, and we can solve the Hamiltonian equations, and we can write down the trajectory again as some inertial motion, where we have a propagator here. So basically the Green's, or it is the Green's function of the Hamiltonian equations of motion. And then we have this part which includes the interaction. And as you see, the interactions include, besides the Green's function, also a force. So this is the force between particles. Right. So as I said, we always deal with an ensemble of very many particles. And so we usually just, as a shorthand notation, we can just write the trajectory for all particles in a tensor notation, but so the structure remains the same. So we have an inertial motion and we have a part that contains the interactions between all particles. Right. So in the end, we're not interested in the generating functional, but in properties, in macroscopic properties of a system, which is, for instance, the power spectrum. And so we need to compute correlation functions from the generating functional. And we do this by applying suitable operators to the generating functional. And so, for instance, we define the number density operator like so. So we start off with the number density, which is just the sum over the Dirac delta of particles sitting at some position. We take the Fourier transform thereof, and then we replace the particle positions by functional derivatives with respect to the source field J that we introduced before. And if you remember, J couples to the particle trajectories or particle positions and momenta in the end. And so if we apply this density operator to the generating functional of kinetic field theory twice, so if we want to get the two-point correlation function, we can compute the density power spectrum. Okay, in the end, the source field J is set to 0, as is the usual case. All right, sorry. Right, so we now know how to compute the power spectrum, but we still need the full solution to the trajectories of all particles. And as you know, if we have a system of many particles that are interacting, we're not able to really know where each particle is at any given instance of time while they are interacting. So what we can do is to compute the inertial motion of the particles exactly, because it's just propagated by the Green's function. But for this interaction part, we will need to make some kind of approximation. So the first thing one can do is, well, to say we have simply Newtonian dynamics. So we know our Green's function, we know the propagator. And then it is possible to resum, so to define a perturbation series such that we're able to resum an infinite subset of interactions into a macroscopic propagator. And we can then express the density power spectrum as some tree level contribution and then loop corrections. And they already include parts of the interaction between particles. So even the tree level does. And the really cool thing is that from Newtonian dynamics, so basically just particles moving on an expanding background, we can compute the full linear growth of the power spectrum up until, well, k to the, I would say, 50, 30, I don't know. But so to quite small k. In the end, you see the linear growth drops, so the growth drops down because we are not including loop corrections, but already at tree level, we can, on on larger scales, we can reproduce the full linear growth of the power spectrum just using Newtonian dynamics. And to our knowledge, this hasn't been done before. So, but, well, you're not only interested in linear growth, you want nonlinear growth of structures. Oh, sorry. Just to, as a side remark, I'm showing the results for cosmology now, but kinetic field theory isn't really tuned to cosmology. You can also study laboratory systems with the theory, which we have done. So we have basically applied the theory to completely different initial conditions, to a different kind of interactions. So we used short-range interactions, and we use this resummation scheme to include interactions now, which is called resummed KFT, which I just talked about. And so the system that we looked at were a system of Rydberg atoms. They have a fun property that if you excite an atom into a Rydberg state, which means that the principal quantum number is quite large, so the electron is pulled away from the nucleus, and you have a tiny dipole. And this tiny dipole will shift the excitation level of its neighbors by a certain amount so that these cannot be excited by the same frequency. And so you can only get these highly excited Rydberg atoms at certain distances. Okay, so twice the so-called Rydberg blockade radius. And so effectively, so when you excite ground state atoms into Rydberg states, and you look only at the Rydberg atoms that you've produced, you have effectively created an anti-correlation between these atoms. And they interact via a short-range potential. So we chose Gaussian form because we're theorists, and it was the easiest one. And you could study their dynamics. And here I'm showing a plot. So this is the initial anti-correlation function of the atoms. And the solid lines represent numerical simulation. And the dashed lines are KFT results. And what you see, so for different times. And what you see is that KFT can reproduce the dynamics of this laboratory system quite far into the regime where non-linearities will have a stronger effect. And here one would then need to compute loop corrections, which we are at the moment. Right. So let's get back to cosmology. So I've shown you that with the resummation scheme for KFT, you can use Newtonian dynamics, and you can, at least on larger scales, recover the linear growth. But if you want to compute nonlinear structure growth, then either you need to work out loop corrections in this resummed kinetic field theory formalism, or you can put part of the interactions into the inertial motion of your particles. So you can make a clever choice of the propagators that you use for your inertial motion. You can, for instance, choose the propagator such that you reproduce linear growth. So you make a transformation that the propagator is now the difference between growth factors at different times. This is what we call then Zeldovich trajectories. You can then improve on these trajectories by introducing a slowing down of the re-expansion of structures. So you can basically prevent structures that have formed so that they don't just dissolve against it at the stream. The particles don't just fly away, but are retained. But if you do that, so if you introduce part of the interaction into the inertial motion, you need to account for that in the interaction term later on. So you need to compute the relative force. So this will be the full force, and then you need to subtract the fact, so the part that you used in your inertial motion already. Okay, so that's so as to keep the whole formalism consistent. Right. So another way to then get to the nonlinear power spectrum would be a perturbative approach. So here we can just rewrite the generating functional of KFT in the form where we have a free generating functional, meaning that it includes the inertial motion only. And then we have an exponential with an interaction operator, which is then suitably defined. But the expansion, the perturbative expansion is then in terms of this interaction operator. So we expand this exponential, and then we have the first order will be just the free evolution of particles, and the second order will then contain something where you apply the interaction operator on the free generating functional, and this will be to first order in the two-particle interaction potential, and so on. And then you can again apply the suitable density operators that we've defined before and compute the density power spectrum. So if you do that to first order only, then this is basically the result that you get. So here we're comparing the KFT result up to first order, which you can see in red, to the nonlinear power spectrum that we got from Cosmic Emulator. And here is the relative difference. So you see in this very naive perturbative approach, just the first order, doing quite well, but on intermediate scales, you get quite a large deviation of up to 35% probably. So in order to get better here, you would need to compute higher order perturbative corrections. But the issue again is that, as you know, if you do perturbation theory, each term gets larger and harder to compute. And so we have basically looked for another way to include particle interactions, and we have now defined a so-called mean field approach, where we evaluate the interactions between the particles, so the force between the particles beforehand, and so we have basically a multiplicative factor that includes particle interactions, which is multiplied with the power spectrum, which includes only inertial trajectories. And this interaction term, well, it contains the two particle interactions and these forces between particle pairs are weighted by the correlation function to produce a net force between particles, because in a homogeneous universe, if you computed the force that each particle feels from interactions between all the other particles, you would get a net force of 0. But the particles are correlated, and if you weigh the force between particles with the correlations between the particles, you will end up with a net force. And this is basically what we compute. And if we do that, we get a closed expression. So we don't have a perturbative expression now, but we have evaluated this factor basically in this mean field approach. And so this is the result. It differs a bit from our last paper because I used the same trajectories that you've seen in the perturbative approach in the slide before. And so what you see is that on intermediate scales, we get better results, but at smaller scales, the results get worse because in this regime, the damping factor that is included in the in this free power spectrum needs to be counteracted by the interactions in this factor. And if that balance, due to our averaging procedure, is no longer given, then the damping will take over and damp away structures here. So there are ways to compensate for that, which you can find in this paper. But here I'm showing a very naive way to do that. And I think it's still a good result. Right. So you've seen the most important results for the power spectra now. And I would like to now show you a little bit in depth what the advantages of the particle-based approach in KFT are. And so I would like to compare kinetic field theory to the Eulerian standard perturbation theory, which is based on the fluid equations. And as in KFT, you can also formulate SPT in terms of a generating functional. So this has been done before, and so we're just going to use this formulation because it's closer to what we do in kinetic field theory. So in kinetic field theory, the generating functional is formulated in terms of point particles and the trajectories of those particles. In standard perturbation theory, on the other hand, the generating function is formulated in terms of an averaged fields. So the velocity field and the density field and the equations of motion of these averaged fields. So in kinetic field theory, we will need the solution. We need the solutions to the Hamiltonian equations of motion that we've seen before. And for SPT, we use the fluid equations. And in both cases, you can again apply appropriate density operators, for instance, to get statistical properties like power spectrum, bispectrum, and so on. Right. So we're going to use the fluid equations, and I would just now show what happens even before we compare the two approaches on this level where we use the fluid equations, that information is already, or part of the information is already used as soon as we use the fluid equations in the SPT formalism. And so the first step where information is lost is if we start with the Vlasov-Boltzmann hierarchy that contains all the information about a particle ensemble. In order to arrive at the fluid equations, we make a finite truncation of the Vlasov-Boltzmann hierarchy, and we end up with these equations. But because we truncate the hierarchy, we neglect information that is contained in all the other higher moments of the phase-space distribution of the particle ensemble. So this is part one of where the information is lost when we're doing standard perturbation theory. The other, and far worse, is that in order to solve the fluid equations, we usually set the velocity dispersion. So this term here, we set the velocity dispersion to 0. This is known as the single stream approximation. And the assumption behind this is now that the system is described by a single valued velocity field at every point. This is true up until the point where streams start to cross. At that point, this assumption breaks down, and this is what the shell crossing problem is referring to. Another simplification that is made is that the velocity field is vorticity free initially. With this assumption is fine, but since we have neglected the velocity dispersion, we have also given up the opportunity for a vorticity of the velocity field to arise, because the velocity dispersion term could source vorticity. We don't know how large the effect would be, but it's just a further simplification that goes into the fluid equations. So now when we do Eulerian SPT, the generating function of SPT includes the fluid equations, and as we've now discussed, we have the truncation and the single stream approximation, which already leads to information loss. In kinetic field theory, up to the point where we plug in initial conditions and write down the generating function with the particle trajectories like so, it still contains the full information. So now let us compare the perturbation theories that we do for kinetic field theory and for standard perturbation theory. So for kinetic field theory, as I've shown you in an example, we expand in terms of the, for instance, the interaction potential. And what we actually do is the perturbation theory in KFT is set up in terms of deviations of particle trajectories from inertial trajectories due to interactions between the particles. So the perturbative corrections arise due to particle interactions. And we can actually give an exact result, so we can give an exact expression for the generating functional if we simply use the free theory where the interactions are switched off. In the case of SPT, the perturbation theory will not be in terms of the interaction potential. So linear theory in SPT describes the independent evolution of Fourier modes, and even linear theory will in general include interactions already. And then these field modes are coupled by nonlinear source terms, and this is what produces perturbative corrections. And by construction, as we've seen just before, even the linear theory will not be exact in SPT, whereas in KFT we can give an exact expression for the field for the free theory. So because the perturbative schemes are so different, it's very hard to compare the perturbative expansions in KFT and SPT when interactions are switched on. So what we do is, to compare the two, we switch interactions off, okay? And so that means, in terms of KFT, in the particle trajectories, we'll just neglect this term and keep just the inertial motion. And as I've said, we can then compute an exact expression for the density power spectrum. It looks a bit scary, but it can be very well evaluated. So the only things you need are the propagators, and these objects contain initial correlations, and so this can be fully specified if we know the initial power spectrum, which, as I said, we'll usually take to be at the point of to be the CMB power spectrum. Right, so we will now be treating everything in this free streaming limit where interactions have been switched off. If we compute this expression now, so if we evaluate that, for KFT, we can see the following. So in the free streaming regime, kinetic field theory contains the full information about the particle ensemble. And what we can see is that at early times, so this is the free power spectrum compared to the linear one. And we can see that at early times, we have a build-up of structures on small scales, and this bump will propagate in time to larger scales, but at some time it will also be washed out. And this build-up of structures and then them being dissolved later on indicates shell crossing, which in KFT is not a problem because we work in phase space. So in the free streaming regime, so in the absence of gravity, kinetic field theory represents basically a resummation of all perturbative corrections due to the nonlinear kinematics of SPT. And in the free streaming regime, we believe, so because KFT contains still the full information of the particle ensemble, it should be a better starting point for a perturbative treatment. And we can recover terms of standard perturbation theory if we expand the free streaming, the full KFT result in the free streaming limit. So for instance, if we expand this expression here, so this one, to second order in the initial density power spectrum, we will get the free streaming one loop result of SPT. So this is what is shown here. So in black, you have just the linearly evolved power spectrum. You can ignore these terms, they are just contributions to this dark blue line. And the dark blue line is the SPT one loop result. And the red line is the full kinetic field theory power spectrum in the free streaming regime, so where interactions have been switched off. And if you compare these two, you can see that KFT, so the full power spectrum, is actually strongly damped. So here on nonlinear scales, the damping dominates and the power spectrum will be strongly damped. So if you would switch on interactions again, then what would happen is that the interaction terms would actually have first to deal with this damping term, and then the net force that is still left basically would then lead to building up of structures. And so the important message to take away here is that in the free streaming regime, or in the free streaming case, KFT contains the full damping of the theory and is an exact result. And so what we think could also be done, so not only is it a better point to start a perturbation theory from, but we also ask, so is knowing the full theory, the full free streaming theory, and knowing the full damping of the system at least, can we then use this to construct non-perturbative solutions for the full system with interactions? So one example of an attempt to do so was this mean field approach, where we averaged over interactions. But there are probably much better ways to do so. And the second question is, well, we now know how to compare kinetic field theory and standard perturbation theory without, so when we switch off interactions. But the question is, so if we switch interaction back on, what is exactly, how can we make the connection between this microscopic description of kinetic field theory and the macroscopic description of SPT? So I think this will be very interesting. And this is basically, these are the open questions that we have right now. So I'm happy to discuss. Right, and I'm basically at the end of my talk. So let me just summarize. So kinetic field theory is a parameter-free analytic description of nonlinear structure formation. So far, it's been very successful in the linear regime, in the nonlinear regime of structure formation. We don't need to make any assumptions on halo profiles or halo mass functions. It allows us to get a fundamental understanding of large-scale structure formation on a particle level. And we think that the free streaming regime of KFT, since it is exact, is a better starting point for a perturbative treatment. So I will stop at this point